Hi everyone, and welcome to the third and final part of my Blue Planet JavaScript series. In this tutorial we're going to tidy up some code, uncover some bugs, and create an animated radial gradient effect. So what does our code currently do? You can go ahead and download this code from the link in the description below. This is what it does. Blue planet with some stars moving in the background. Okay. So the first bug has to do with the size, the radius of each star. So just down here, see that we're hard coding this value? How about we pull that out first? So we'll create a constant max star size. Now, size to me indicates a diameter. So we'll define this as maximum diameter of each star in pixels. So because it's a diameter, we'll just put it in here. And this is a radius, we have to divide it by 2, don't we? Quickly check that. Yep, looking fine. So go ahead and bump that up to say 100 and reduce the number of stars. We don't want 200 of these things flying around, just down to 10 will be good. And this is where we'll see our first bug. So see the planet on the left there? Dunk, it suddenly teleports to the left. And you'll see it with the other ones as well. Dunk, dunk. That's because we're using the center of the star as its position, and we're not waiting for it to go off screen. So to fix that, we just need to go down to our update function, where we say update its x position. Now all we have to do is, so instead of saying less than 0, it has to be less than 0 minus the radius of the star. So stars I dot radius, right? Okay, so when it's less than that, it'll be off screen. Now for each of these other situations, when it's greater than the width plus the radius, it'll be off screen. When it's less than 0 minus the radius, and greater than the height plus the radius, it'll be off screen. But that's not the end of it. We have to also adjust for that. So we want to add, when we teleport it, we want to add back that radius, but we want to make it off screen, don't we? So it has to be 2 times the radius, so times 2. So this we'll have to do to each of these situations. We'll have to add the radius times 2, just so it's fully off screen when we teleport it. Let's give that a go. Okay, watching the ones on the right here. Okay, that big one that just went off, will it come back on? Yep, it's coming back on. A lot smoother experience. Just do it one more time going a different direction. One goes off, yep, comes back on down there. And this one going off the top right corner, comes back on the bottom right corner. Good. Okay, go ahead and change those numbers back to what they were. So 3 and 200. Now the next issue is that the stars always travel on a 45-degree angle. And that's exactly what we've programmed it to do, because each of the x velocity and the y velocity are identical. But to be more realistic, how about we add in a randomizer? Okay, so down where we have x velocity and y velocity, how about we just throw in a randomizer here, math random between 0 and 1. So that'll just mean that the x velocity is some proportion of star speed. Now in order to maintain this actual speed, then that would be the hypotenuse of a triangle, wouldn't it? So the x velocity is, for example, one side, the y velocity is another side, the speed is the hypotenuse. So to calculate this correctly, we'd have to use Pythagoras' theorem. Do you remember what that was? A squared plus b squared equals c squared. Bit of a maths lesson. So we know that a squared is just x. X squared plus y squared will equal the speed squared. Rearranging to get y as the subject, y squared equals speed squared minus x squared. And finally, to get y by itself, so y will equal, it's the square root of it, isn't it? So it's the square root of all of this here. The square root of the speed squared minus x squared. Okay, so instead of writing star speed here, let's put all of that, put this in here. So we need to use the square root function. You can get that from math. Math square root of speed squared. So that's just our planetary speed. Sorry, our star speed. Star speed. Oh yes, to get the square, we use the math.power function. Math power. The number is the star speed, and we want it to be squared. Square root of that, minus, remember, minus x squared. So x squared is just our velocity, x velocity. Power of our x velocity squared. Okay, so the square root of our star speed squared minus x velocity squared times by a randomizer to get a direction. That should be okay. Let's give that a go. So the stars are traveling that way, going up that way. See, they're almost going horizontal there? So it looks like it's working. And they should always be traveling at that speed. Oh, there we go. They're going downwards there. They should always be traveling at that speed that we've determined here. Let's bump that up a little bit to 25. Remembering we've also added in a multiplier later so that the stars don't go exactly the same speed. So if you look just below there, we're adding in a random multiplier, which is still fine. It's just but our base speed is going to be this. So I think that's working well. Good. Next, wouldn't it be nice if we could set the size of the planet? We'll set it easily. So in the code, we can create a constant called, say, planet size, and we'll set it to a fraction of screen width. So planet diameter as a fraction of screen width. So 0 to 1, we mean, not as a percentage, not 70%, although you could put it as a percentage if you wanted to. And we'll create a variable called planet radius, because that's what we use in our code, more frequently anyway. Planet radius, what does that equal to? So it's the planet size divided by 2, multiplied by, I'll put this here, the canvas width. Canvas width, right? Because we said it's a percentage of, so the canvas width times the planet size divided by 2 is our radius in pixels. Now where do we want to use that? Well, we can go down to where we draw our planet. Here we go. Draw the planet. That's the radius there. So we'll put that in there. And also on the gradient, that's the radius of the planet. Just test that quickly, make sure we haven't broken anything. Yep, that's working okay. Now, but what happens when we modify this size? Let's change it to, say, 0.2. Change the planet size to 0.2. What do you think will happen? Okay, the planet is smaller. A few problems. One, the gradient on the planet isn't in the right position. And the halo doesn't change size to suit, does it? So let's go ahead and fix up the halo. To do that, we need to work out what percentage, so I'll put it back to 0.7. What percentage, what's the ratio between halo size and planet size? Well, look at our halo here. It's got a radius of width by 0.5. Now, if you remember, our planet size was width times 0.35, so the ratio is 0.5 to 0.35, isn't it? So how about we create a variable called halo width, halo radius I should say, halo radius, and that'll be based on planet radius times 0.5 divided by 0.35, because it's going to be bigger, isn't it? It's going to be bigger than the planet. And all we have to do is substitute that in for our halo size. So where's our halo? That's the halo 0.25. I see that. So that's half the size of the original halo. So that'll be halo radius times 0.5, because that was half the size. 0.25 was half the size of 0.5. And the full radius is there. Okay. And that's the gradient for the halo. And the actual halo itself, that's the radius there. Great, let's give that a go. So the full size is okay. What if we change that to 0.2? Yep. The halo looks okay. The gradient's not correct, but we'll fix that up soon. Try 0.5. Looking good. And just go to the extremes. 1. Yep, it's fine. Next, let's fix up the gradient position. So this is more noticeable when the planet is smaller. So put it down to say 0.3. See that the gradient is too far off center? We want it to be the same relative position. So to do that, we can just go down to where we create the gradient, create a gradient for the planet. Currently it's based off a fixed screen position. We don't want that. So we're based off the center of the screen, which is where the planet is, the center of the planet, minus some proportion of the planet, so of the planet radius. So planet radius times, say, 0.2 instead. 0.2. Okay, and we'll apply that to all. So instead of height times 0.4, we'll change that to 0.5 minus the planet radius. And here is the same thing. Just go ahead and update it all. And here is the same thing. Okay, let's see if that works. So hopefully the radius will be in a better position here, the gradient. That looks okay. And if we change the size, it should be in the same relative position, say 0.5. Yeah. Great. And back to our original size, make sure it looks okay. Great. Next, we'd like to get the gradient moving. So in order to do that, just copy the current x location of the gradient, go up to the top, and we'll create some variables. We'll create the location of the gradient, so gx, gy, and the velocity in each direction. So the velocity in the x direction, so gxv and gyv. And we'll set them up, say down here. Set up gradient parameters. So gx will just equal what I have in the clipboard there. Gy will be very similar, just we'll be using the height instead. Gxv, we could randomize it here, or we could just use what we currently have. So all the stars are going in a random direction, aren't they? So why not have our planet going in the same direction? So we'll just use the first star dot xv. And similarly for the y direction, .yv. Right, now to apply this, we'll have to go down to where we set our gradient. Let's update all of this. So this will have to be the gx variable now, and this will be gy. This will make this all look a bit simpler too. Gx, gy, and this will be gx and gy as well. Gx, gy. Good. And here we'll update the position. I'll update the gradient position. So that'll just simply be gx plus equals gxv. and gy plus equals gyv. And hopefully we'll have a moving gradient. Let's try it. So yes, we can see the gradient's going down with the stars, like in the same direction as the stars. But what do you think will happen once it goes off the planet? Because we've put no code in there to tell it what to do, it'll just go off and never come back. So it'll be a permanently dark planet. So we'll fix that up now. So go back to our code. Now the first thing we want to do is identify the center of the circle. Now we do know where that is, but we haven't got a variable for it. So create two variables. Cx will equal canvas.width times 0.5. We've used this throughout our code, so we'll go and clean all that up soon. And cy will equal canvas height times 0.5. So anywhere we reference that, we'll change that to cx and cy. It's mainly done in our update function, I think. Oh, there's one there where we set up our gradient. Cx, so set up our gradient parameters, change those to cx and cy. It wouldn't hurt if you didn't do this, but it's just cleaner. And inside our, where we create a gradient for the halo, we can cx, cy, cx, cy, and here as well, cx, cy. Good. And down here where we draw the halo, cx, cy. Looks a bit cleaner now, doesn't it? And finally, just where we draw the planet, cx, cy. Great. We should have done that initially, I think, but oh well. We also need to know the angle of travel of the gradient. So let's create a couple of variables here. So the g angle, the gradient angle. And we also want to know the length of the sides of that right angle triangle. So we know the hypotenuse, we just want to know the x and y components. So we'll call that gxd, from lack of a better, like d for distance or whatever, and gyd. So they'll be the sides of our movement triangle, our velocity triangle. So where we set up the gradient parameters, we need to calculate the angle, which we can do now, because we know the x velocity and the y velocity. So the angle will be the inverse tan of the opposite over the adjacent, if you remember your trigonometry. So to do that in JavaScript, just go math atan, that's the inverse tan or arctan of the opposite. Now we should use the absolute values here because they could be negative in that they'll be traveling in different directions. So we'll use the absolute values to keep it all absolute. So the absolute value of the opposite, which is the y component, gyv, divided by the absolute of the adjacent, opposite over adjacent, which is the x component, gxv. That'll give us an angle in radians. It doesn't really matter what it's in, but that's what it will be in. And to calculate the distance traveled across the planet, well, we just multiply the planet radius times the cosine of that angle. Cosine is the horizontal, or the x, if you remember your unit circle. So g angle. Similarly, the y component going across the planet, so going up the planet, will be the planet radius times the sine of that angle, the vertical component. You might just have to trust me on all of this. But yes, if you know maths, that's what cosine is, the horizontal, and sine is the vertical. You might be asking, why do we need to know all this stuff? Well, we just need to know when the gradient is going to be off the planet. So we need to know all this. So go down to where we update the gradient position, and we'll have to put in a couple of conditions here. So gxd and gyd could be 0, in that there could be no motion in the x and y direction. So we should use the larger of the two. So if gxd is greater than or equal to gyd, then we'll do something. And otherwise, we'll use the gyd for our calculation. So here, inside the x So this is when gxt is larger. Well, if gx is larger than the center plus the gxd, that means the gradient has reached the edge. Well, that means the center of the gradient has reached the edge. So we want to multiply that by 2 in order to get to make sure that the gradient is fully off the planet. Or that's in the positive direction. It could be that it's going off the left of the planet. So gx is less than cx minus gxd times 2. So if any of those two conditions occur, we'll do something. So how about we create a update gradient position, whatever. Okay, we'll create a function. We'll handle that soon. Similarly, this is for when gyd is larger. We'll need to update all of this to be for gy. So gy is greater than the center y plus gyd times 2, or gy is less than center y minus gyd times 2. So either of those positions will do the same thing. We'll update the gradient, we'll move it to the other side of the planet. So go ahead and create this function. Just down here, function, update gradient position. Now, all we need to know is if the gx, so if gx is less than the center, so that means it's on the left, it's gone off the left of the planet. If gx is less than the center, we'll do something. Else, we'll do something else. Now, what will we do? If it's less than the center, we want to jump it to the right, don't we? So gx will equal the cx plus the gxd times 2. So we're just jumping it to the other side. There's other ways you could simplify this code, but it might be less readable. Else, it'll be the cx minus gxd times 2. So all of this is for update x component. Similarly, I should say, you can update the y. So if gy is less than the center y, that means it's gone off the top. So we want to add twice the y direction component. And here gy equals cy minus gyd times 2. Right, let's give that a go. Okay, how about we speed this up? That's going a bit too slow. So go up to change that to say 35 star speed. So we can see the gradient zooming off the edge. There it comes. It jumps back to the other side and travels back down. So it looks like the appearance that we're trying to achieve here is that the planet is rotating. Try it again. Yep, so it's following the stars, going round and round. You could, of course, update any of these parameters. You could change the direction of travel. You could make it go crossways or reverse it. For example, if we went in and changed the what? Here we go. So the gxv and gyv, that's the direction of velocity. You could change one of them to a negative, say. What does that do? Yeah, or you could even change gxv to equal yv, so negative yv, and change this to equal xv to get it going crossways, I think. Yep, so it'll be going across the motion of travel. Have a play. But otherwise, that's the end of our tutorial series. I hope you've enjoyed it. It got a bit complicated there in terms of maths, but it's good to revisit these things sometimes. Okay, see you next time. Bye.